Welcome everyone. We're talking chapter 3, section 4, polynomial functions with graphing, application, and models of those. Okay. And our focus is going to be graphing polynomials that are degree 3 or greater, basically. Degree 2 is pretty straightforward. We've seen a lot of quadratics and a lot of parabolas by this point. So most of that information will be pretty familiar to you. And we're going to focus mostly on degree 3 and higher, which are other polynomials. Essentially, if we follow the notes and look down here, figure 20 is talking about odd degreed functions, so things that have a degree of 1, 3, or 5, or so forth. And they each have some similarities to one another. One of the key pieces is, of course, going to be our domain and range. Now, domain for all polynomials is the same, negative infinity to positive infinity, or just all real numbers. However, odd functions can be deemed to be increasing over their entire domain. Okay, now, odd, I mean odd degreed function. Okay, now these baseline ones can be determined to be an odd function, which means they also get to have origin-related symmetry, but we don't need to focus too much on that right now because these are just kind of the basic parent functions. They will be transformed, shifted, stretched, and moved around before we graph these new ones. Okay. Similarly, we can study even functions, and you'll discover something pretty similar. That domain is the same between all polynomials, but our range is kind of limited in this case. These kinds of functions can have a minimum or a maximum value, and you'll notice that both ends are going in the same direction. So most of these have been marked as going upwards. If you were to reflect them, then you would discover that they can go down as well. Okay, so these are again based off of even degrees. Even functions demonstrate y-axis symmetry, okay, which means left and right side can match up. You'll notice that these actually have a increasing and decreasing section. So we can't say which one is happening until we look at our graph, but each one has a section that is increasing and then another section that is decreasing. Okay. All right, so we've looked at some of the graphs. We've just talked a little bit briefly about domain range and increasing, decreasing intervals. Let's take a look at this in depth a little more. So one of the key things we're going to notice is that the a value, that constant that is multiplied in the front, is going to be your stretch or shrink. Now, this is common to all functions. We've seen this before. So a function with a large number in the front is stretched vertically and makes it narrower. And a function with a small number or a fraction in front makes it smaller, flatter, and wider. Okay. And then we've kind of seen all of these transformations before. The up and down movement, and adding a negative is of course going to cause your graph to reflect. So either flip the graph over, make the ends point in the opposite direction that we would expect them to. Let's look at some examples with transformations, and these are going to be based off of the graphs we saw in our previous figures. These might be a little bit of a rough sketch, but they follow pretty much what we saw in the pictures above. Okay, so let's just start with x to the fifth minus 2, and what you should determine is this graph is, of course, a x to the fifth function that has been shifted down 2 spaces. And so my center point is actually going to be like 0, -2, and we can roughly guess how it's going to go. So this is, of course, not a perfect graph, but just a rough sketch of what my graph is doing. Okay, now this being an odd function, right? This is an odd degree, which means this function is actually increasing always. So we will be increasing from negative infinity to positive infinity, which is again the entire domain of this function. Okay, and so again, roughly, I was careful to make sure I got this point correct, 0, -2, which is that downward shift 2. The next point is 1 space away, like 1 to the fifth power is still just 1. And then it exponentially is going to increase how fast it's moving. Okay, but roughly this is what that graph looks like. If we move on to example B, okay, we're going to see, hey, this is now an x to the sixth function, but this plus 1 being inside the parentheses is going to make us move left one space. And so let's go ahead and mark that. This is my center. And a even power, an even degree, means that our ends are going to move in the same direction, kind of like a quadratic. So this is actually very similar to a quadratic function. It, of course, increases much faster than a quadratic because instead of being squared, it's to the sixth power. So how about where this function increases and decreases? So let's see, where are we increasing and where are we decreasing? So our function is increasing in this section that I'm highlighting in yellow. And so if you're increasing there, that of course starts from this center vertex point, which is in this case at -1 and going towards infinity. And so that is our increasing interval. And then the reverse applies to our decreasing interval. Okay, so here's my section that is decreasing, and you can see that goes from -infinity to 1. And there you have it, guys. That is the interval where we're increasing, decreasing. And you can see because the graph has an even exponent, I made sure to point those both going upwards. Even degreed functions, you should think of like a quadratic. They are going to have both ends going in the same direction. By default, they both go upwards, like this graph, but if you were to reflect it, they would both go downwards. Okay, studying our last function here. Note that this is to the third power. It says 6. There's a bit of a typo on my notes here, but it is to the third power, which means we can at least determine that both ends should be going in opposite directions. Okay, so let's look at some of the transformations first. So I'll just move from right to left. I see this +3. That looks like we're going up 3 spaces. -1 inside the parentheses is going to go right 1 space. Okay, and then this -2 in front. So we have a vertical stretch by 2, and then the negative is going to cause us to reflect over the x-axis. Okay, so there's quite a few transformations going on here, but let's start with the first two, which are going to find us the center of this graph. So go right 1 space, and then let's go up 3 spaces. So here we go, right 1 and up 3. There we go, right there is my space. Now, I have a stretch by 2 and I'm reflected. So normally my graph would point like this, downward for on this side and then upward. But because we have that reflection, our graph is actually going the opposite direction. Okay, and so instead, our graph is going to go upwards this way, and this one is going to be coming downwards. And I'm going about 2 spaces down on the first one. Okay, so I'll draw this a little nicer, but at the same time, what you can see is we're using the transformations to understand the basic behaviors of these graphs. It's not perfect, okay? We can plug in points to find more information, but this is purely based on the exponent and the transformations and knowing about what the original graph looks like. Okay, again, let's do that increasing, decreasing thing. So what do you notice about this graph? I'm hoping that you realize that the whole graph is going downwards. Okay, even though it kind of switches its curve in that center point, it's still decreasing. So it went from increasing everywhere to decreasing everywhere instead. So this is an odd degreed function. Normally, I would say it's increasing everywhere, but that reflection does change a lot about this. Okay, it's going to change it to be decreasing everywhere. Okay, so Domains of polynomial functions, guys, every single domain is the same for us here. They are all going to be all real numbers, negative infinity to positive infinity, okay? They're smooth curves, they're connected all the way throughout. There is no break in there, okay? Now, this is one of the interesting points of analysis here. We point out that odd functions, no matter how you organize it, because of their nature, the fact that they go in opposite directions, they will always cross through the x-axis at least once. There is at least one x value that will have f of x equal to 0. No matter what, every odd degreed function must pass through the x-axis. And that's one of the interesting points about this. However, even functions do not necessarily follow this rule, okay? They could have one solution, many solutions, or no solutions. However, they have their own special limitation, which is on range. Okay, they will always have a minimum or a maximum value in their range. Okay, and so sometimes it's based on a vertex, sometimes it is more complicated than that, but we can always find some kind of minimum or maximum value. As you can see in Figure 26, these have either a maximum value or some kind of minimum value to them. Okay. Now, what does we mean by having different zeros? Okay. Well, these functions are made up of multiple smaller factors that are multiplied together. So, for example, this expression that's given to us here in the middle of the page is a polynomial. It has a total degree of 6, okay? So let's make a note that the total degree is 6. But individually, we can see it's made up of these three factors, x plus 2, x plus 1, and x minus 1. And each one of them represents an intercept on the x-axis, okay, or a 0 or a solution, whatever name you want to use here. Now, because they have different exponents on them, they are each going to cause something different, and we'll use these behaviors to help us visualize what our graph looks like. So the first thing, a multiplicity of 1, okay, that means our graph crosses the x-axis, okay, which means basically at this point, negative 2, 0, you're drawing a line straight through that point, okay? And then our next one is, of course, a multiplicity of 2. Now, what does that mean? That means that my function is a square on that function, okay? And they give this term tangent to it, but realistically what it means is it bounces off of this point, okay? It's going to turn at that point when it makes contact with the axis, okay? And this looks kind of like the vertex of a quadratic. So roughly, it would look something like this. So here's your x-axis, and your function comes down and bounces off of this point and turns back the other way. Okay? And it roughly does something like that. Whereas the first degree function, you have your x-axis, and your line would just go straight through it like at that point. Okay? And let's take a look at this last one. The last one has a multiplicity of 3. And so a multiplicity of 3 is kind of interesting. It's similar to a multiplicity of 1. And if you think about why, it's because they are both odd values. Okay? So we've got this thing where they kind of mentioned that it does two things. It crosses and is tangent to the point, and that's very hard to visualize. But if you think of it as a cubic function, you can see what it does at that point very easily. So here is my axis again, and a small visual. So my cubic function, if it went through here, might go down in one direction this way, and it changes its curve the other way, okay? And this term can sometimes be called a change in concavity. They mention that vocab here. So if you ever hear concavity change, this is what it means. It's like literally the function changes the direction that it is curved in. Okay, and you can see this looks very similar to the cubic graph, and that's how we remember what it is. Okay, so we will use these three shapes to help us graph these functions in the future. Okay, so again, you can kind of see the shapes reiterated here at the top of this page. So again, this is something like with a multiplicity of 1, so maybe something like x plus 1. Okay, this second one is a even multiplicity, so something like x plus 1 squared. And then our concavity change, the third one, would be x plus 1 to the third power. Okay, so any even or odd will resemble those last two. And you can see exactly, we see that 1 point touch on each of them is just the behavior at that point that we really care to see. Okay, turning points. And turning points is literally exactly what it sounds like. How many times can your graph change directions? Okay, and it's always n minus 1 turning points based off of the degree n. Okay, so just whatever your degree is, one less turning point than that. And behaviors, these are also based on if your function is an odd degree or even degree. Odd degrees go in opposite directions, even degrees go in the same direction, okay? And so the default is for odd, negative on the negative side, going upwards, positive on the positive side. And then the second version is the reflected version. So if you had a reflected polynomial, it would be flipped over, and this would be case B. So let's make a quick note here that this is the reflected version. Same with part B over here. This is reflected. Okay, and the original is version A. Okay, so the degree we always look at is the highest exponent term. Okay, it's always the most important term. The other degrees kind of fall secondary to that, and so they do not matter. They only change the middle of the function, but never the ends of the function. Okay. Okay, so in this example, let's use what we know about the end behavior and directions of the functions to match them up with a graph, okay? So let's start with the first one, x to the fourth minus x squared plus 5x plus 4. So this has an even degree, and it is positive. So we know that both ends of this are going to go upwards, like it's a quadratic. And so if we look at our graphs, this one must actually be graph C, because that is the only one where both ends are going upwards. Okay. Similarly, let's go look at part B. Part B is even again, but this time it is a negative. And that just means that the two ends are going to be going downwards. Okay. And so let's look for a graph where both ends are going downwards. That's going to end up being graph A. Okay. And let's try out graph C. So function C is an odd exponent this time, odd degree. And it is going to be a positive. And so the two sides are going to be going in opposite directions, down first and then up on the other side. Okay, and if we look, that's going to be graph B. And finally, we've got an odd graph that is negative. And so basically, again, the ends are going in opposite directions, but this time the left one is going upwards, the right side is going to be going downwards. Okay, and so this will end up being graph D. Okay, so basically just using the degree and whether it's positive or negative to help us judge the direction of the ends of the graphs. Okay, so that's that. Okay, so let's see if we can create a slightly more detailed graph using a function. The key points we're going to use are going to be our zeros or intercepts, and then we're also going to use our y-intercept, and we'll see the behaviors at each point and the end behaviors to try and make a fairly detailed sketch of this graph. Okay, so the first thing is we're going to need to break this function down, and we can do that by factoring. And in this case, we could try something like factoring by grouping, but that doesn't really work. So what we'll do is we're going to use our rational zero theorem. So possible zeros. All right. And so we'll use our P over Q, and we're going to discover that it's going to be some combination of 1, 2, 3, and 6, the factors of 6 divided by the factors of 2. Okay. And any combination of that might have made one of our zeros. So it could have been something like plus or minus 1, plus or minus 2, plus minus 3, plus minus 6, and plus minus 1/2, and 3 over 2. So these are the possible zeros. Okay. And what we'll do is we'll do synthetic division to help us figure out which one it is. We'll start with an easy one, that is 1. Okay. And so our synthetic division is going to go like this. 2, 5, -1, -6. Bring our leading down. Multiply, add, multiply, add, multiply, add. And you can see we got 0. Very good. So our first factor was x minus 1. Okay. And we have 2x squared plus 7x plus 6. And now let's continue to break this piece down. And we can factor that using grouping or whatever method you want. And we should get 2x plus 3 and x plus 2, along with our x minus 1. So we factor that piece down, and now we can kind of see what our roots are going to be here. So we have some roots from each of these factors. We've got x equals 1, x equals -3 over 2, and x equals -2. So let's mark these on our graph real quick. So here we go. We got x equals 1. That's at 1. Then we've got -3 over 2, which will be like -1.5. So I'll put my dot like right there. And then, of course, -2, which is just a little bit past that. So those are kind of close together. It may be a little hard to see, but those two are the last two. They're going to be close together. Okay. Now let's look at our degree and the end behavior. So we have a degree that is 3, which is odd, and it is a positive term leading it. So we're going to have the rising end on the right and the falling end on the left. Okay, remember, this is the default direction. If it's negative, then you flip it over. Okay, so I'm going to add these arrows in actually on the graph as well. So this is going downwards. This side is going up. Okay. The other key point that will be worth finding out for us is going to be our y-intercept. So y-intercept is basically when x equals 0. So we'll find f of 0 and just put 0 in for the x values. I just went back to the original equation and did it. You can plug it in even in the factored form. But it's pretty easy in the original because you'll see something very nice happens as you work this out. And so basically all the pieces that are 0 cancel each other out, don't they? Boom, boom, boom. And we've got something like this, 0, -6 as my y-intercept. Okay, so let's throw that on our graph as well, 0, -6. And the rest is really just connecting the dots now, okay? So we're going to connect the dots like this and just go from end behavior here. I'm going to come up just barely over that line, come back down so that we can touch our y-intercept, come back up this way, and go upwards. Okay, and I'm just going to, this end behavior wasn't in a great spot, but it doesn't matter. Okay, and that's roughly what this graph is going to look like. Okay, the graph is, of course, a sketch, guys, so it is kind of not necessarily the most accurate, but it's got all the zeros and we've managed to get our y-intercept and everything in the correct spots. Okay, So this one was pretty simple in the sense that all of the zeros that we had a degree of 1, and that means the behavior is the same for each one. The line just draws straight through it, okay? But when we look at our next example, you will see they've given it to us in the factored form, but we have one now that has a degree of 2, and that's going to change the way this looks, okay? So let's start by doing this. Let's mark our zeros on here again, and the zeros are going to be 1, 0, 3, 0, and of course, negative 2, 0, okay? And so we can mark these three on our graph. So here we go. Here's 1, 0, then 3, 0, and negative 2, 0. Okay. And a few other things we're going to want to find, of course. Let's start talking about that degree in this case. Okay. So what is the degree for this one? The degree is going to be 1, 2, and then this one counting twice, right? Because of that. So degree is going to be 4, which is even. And you see that this is going to be a negative. So what does that tell us about the end behaviors? The even and its negative, both sides of the graph are going to go downwards. Okay, so let's add some downward arrows right here. Okay, now let's find, of course, our y-intercept. So the y-intercept, remember x is going to equal 0, so let's plug that in. We've got negative 0 minus 1, 0 minus 3, and 0 plus 2 squared. Okay, so negative, negative 1, negative 3, and 2, which is squared. So if we compute this out, we should get negative 12 as our y-intercept. So we've got 0 comma negative 12. And let's go ahead and mark that. Now this sticks off the graph a little bit, but I'll go ahead and put it right there. And now that we've got all these points, let's figure out how our graph is going to look. So one thing that we should pay attention to is, of course, this square, which is affecting my negative 2, 0 point. Now that has a multiplicity of 2, right? So what we're going to do is that means that our graph makes a bounce shape here, and it basically looks like the vertex of a parabola on that point. And so basically we're going to connect this, and it's going to go up, and we're going to touch the negative 2 but turn back around, okay? And so it'll come back down, and I'm going to draw that line connecting all the way down here at negative 12, right off of my graph a little bit, okay? And then we're going to turn back and go up to this 0, okay? And curve up, turn back around, and maybe connect to my end behavior, okay? And so you can see, like, I touched up my end behavior a little bit so that it's easy to see, okay? But the line is going to pass through all of the points, 1, 2, 3, and then my y-intercept, and it's going to match the end behaviors. If for some reason it's not fitting into all of the constraints, so if for some reason you're like, wait, it's supposed to be even, but suddenly my ends are going in opposite directions, or my arrows are pointing the wrong way, or I'm not able to hit one of these zeros, something's wrong and you need to go back and make sure everything is in agreement. So go back and check your work if you run into something like that. Okay. So this is kind of the basis for how to graph these polynomials. We're going to rely on the roots, their multiplicities on each of the roots, which are going to determine their shapes at those points, right? So some things to remember, a single is going to draw a line straight through there, while a 3, 5, 7, 9, a higher degree odd, it actually makes like a curve shape there. And then an even function, anything that's 2 or 4 or 6, makes it bounce off and turn around like we did on ours, okay? So I'll actually make a little note here that this is our bounce shape, which is because of that multiplicity 2, okay? All right. Well, that is it for section 3.4 and the graphs of these polynomials. So again, it's using some of the tools that you've seen before, which is the root theorem to find the zeros, using synthetic division to help you break the polynomials down, and then using that information to plot your graph. Okay. Good luck and happy studying, everyone.